right? The one that's captivated us for thousands of years. It's in our science, our stories. It's fundamental to how we see ourselves in the cosmos. And it is the single epic motivation behind this entire billion-dollar mission. Because, to find other worlds, to search for tiny signs of life across unimaginable distances, the tools we have just won't cut it anymore. We need to build something totally revolutionary, a whole new kind of eye on the universe. So, what really makes this telescope so special? Let's try and get a sense of the sheer power we're talking about here. Because this isn't just a little upgrade, it's a fundamental leap, a complete transformation in our ability to see. To really wrap your head around the scale of it all, just think about this. The ELT's main mirror will gather 100 times, million times more light than your own eye, and it's going to see the universe with over 5,000 times the clarity. I mean, that's a level of vision that's almost impossible to even imagine. Now, if you're going to build the most advanced observatory ever, you need the perfect spot. And kind of funny, the best place to look for other worlds, well, it looks a whole lot like one itself, a desolate, extreme environment right here on our own planet. We're heading to the Atacama Desert in Chile. This is a landscape so otherworldly that you'd swear you were stepping onto Mars. And it's here, in this vast, beautiful emptiness, that we're placing our giant eye. So why here, of all places? Well, it really comes down to the sky. The Atacama Desert gives us an incredible 320 clear, cloudless nights every year. Compare that to maybe 100 in the best spots in Europe. For a telescope, that kind of viewing time is pure gold. But it's so much more than just clear skies. The Atacama is the driest non-polar desert on Earth. There are parts of it that have literally never had a single drop of recorded rain. It's way up at 10,000 feet, miles from any city, so there's zero light pollution. The place is so alien that NASA actually uses it to test its Mars rovers. It's the perfect place to look at the stars, but man, is it a tough place to build something. Building in a place like this isn't just construction, it's more like a war with nature itself. Before a single bolt of the telescope could be put in place, engineers first had to create a place for it to stand. They had to actually tame a mountain. The site they picked was the top of a 3,000-meter-high mountain called Cerro Armazones. The only problem? It was a sharp, pointy peak. So, back in 2014, the team did the only thing they could. They blew the top clean off, removing the entire upper 100 meters of the mountain. That single blast moved an incredible 4.7 million cubic meters of rock. To put that in perspective, that's enough rock to fill more than 1,900 Olympic-sized swimming pools. And all of that was just to create a flat plateau big enough for the observatory. But of course, it wasn't that simple. The blast fractured the mountain's core, and dangerous sinkholes started appearing. So the engineers came up with this brilliant idea. They used huge machines to create artificial vibrations, basically shaking the whole mountaintop to force all the weak spots to collapse at once. Only then could they fill everything in and stabilize the ground. That process alone took 5 years. And remember, this area is a major earthquake zone. So to protect the telescope, it actually sits on a foundation that's totally separate from the dome around it. In between the two, there are these massive hydraulic dampers that act like shock absorbers. So if an earthquake hits, the dome might shake, but the telescope and its delicate mirrors inside stay perfectly still. Okay, so we've tamed the mountain. Now let's get into the telescope itself, because we're about to go from brute force construction to some truly mind-bending technology inside that mirror system. The real secret sauce to the ELT's power is something called adaptive optics. You see, even on the clearest night, our atmosphere makes starlight twinkle and get blurry. It's a real pain for astronomers. Adaptive optics is a system that measures that distortion and then corrects for it in real time, thousands of times every single second. But how do you measure that distortion? Okay, this part is just so cool. The telescope shoots these powerful lasers 90 kilometers up into the sky. They're aimed at a layer of sodium atoms left behind by meteors. The lasers make those atoms glow, creating a tiny artificial star. By watching how that fake star twinkles, the telescope knows exactly how to fix the blur for any real star it's looking at. So let's follow the light. It comes into the dome, hits that huge primary mirror, and then bounces between a few other mirrors. But the really crucial step, the magic, happens at the fourth mirror. This one is deformable. Using the data from that artificial star, it physically changes its shape thousands of times a second to perfectly cancel out the atmosphere's blur.
It delivers a perfectly sharp image to the scientists.
All of this unbelievable engineering, blasting mountains, making artificial stars, it all serves one ultimate goal. It brings us right back to that huge question from the beginning. Only now we have a tool powerful enough to actually find an answer.
To really understand the leap we're making, just compare it to the legendary Hubble Space Telescope. The ELT is going to produce images that are 15 times sharper, and it'll be able to see just that tiny bit farther back in time, 13.5 billion years ago, closer to the Big Bang than we have ever seen before.
And with that kind of power, what is it going to see? Well, it's going to see the very first galaxies being born in the infant universe. But maybe the most exciting thing, it will take the first ever direct photographs of planets orbiting other stars. And not just fuzzy pictures, it will be able to analyze the light coming through their atmospheres to look for the chemical signs of water, oxygen, or maybe even pollution.
And that, right there, is the headline. For the first time, we won't just know a planet is there, we'll be able to see it, and we'll be able to analyze its atmosphere for the very ingredients of life. It's a total game changer in the search for our cosmic neighbors.
And this incredible future isn't that far away. After decades of planning and building, the Extremely Large Telescope is scheduled to see its first light in 2029. Humanity's giant eye will soon be open. Which leaves us all with that one last ultimate question. After all the engineering, the innovation, and the investment, when this giant eye finally stares out into the cosmos, what will it find looking back? Will it be the discovery that finally tells us we are not alone? We can only wait and wonder.